Okay, Food Science and Chemistry Lecture 78, beg your pardon, Lecture 8. Chromatography. Looking at some chromatography techniques. We'll look at general characteristics, paper chromatography, TLC, column chromatography and HPLC, which some of these have already used, of course, in the lab. This is a classic example of chromatography, the separation of colours of a leaf using paper chromatography. Chromatography is essentially a separation technique and is a key step in numerous analytical procedures. Although the original Greek refers to colours, other wavelengths outside the visible region can be widely used as well, can and are widely used. There are many different chromatographic techniques, including the so-called hyphenated techniques like GCMS, which we will look at a bit later. If you look in Blackboard, in Learning Materials, Learn Sky, Chem folder, these are some of the resources that can be found. They can help you with understanding of theoretical and practical issues, and the latter is, of course, very important in the current situation. And we'll have a look at some resources later in the lecture, but for now I'll flag them up for you to have a look at. Okay, moving on. All chromatographic methods have these characteristics in common. This is true from simple paper chromatographic systems to the more sophisticated hyphenated systems. For example, in paper chromatography, the stationary phase of the paper, the mobile phase, is normally water. The sample might be an extract from a plant, and we detect the analytes visually, maybe making measurements with a ruler. So as an exercise, analyse HPLC on this basis. What are the relevant factors based on this analysis? Okay, bring them all in. Sorry, I thought they were all there to start with. Moving on. This is a typical paper chromatography system. Samples are dotted on paper which is placed in water. With the samples above the level of water, it has to be said, otherwise it will just wash off. Over time, the water moves up the paper carrying samples with it, and these may separate into various components. The limit of the ANSI water is called the solvent front. You notice there's a lid. This is used to ensure the atmosphere is saturated with water. This helps with the separation process. So what does it tell us? It doesn't tell us a lot by itself. As normal in analysis, we need standards to compare our results with. As usual, we're mostly interested in analysing substances that we expect to find. However, chromatographic systems can be used as separation techniques, with further analysis being done by other methods, and more of this later. Okay, there's an example of some standards. Okay, paper chromatography, the simplest form. Paper is made of cellulose, and here's a small sample of the molecule. So here's a question for you. Pause the video and have a think about that question there. Which interomolecular groups forces are the OH groups involved in? Should be fairly straightforward. Okay, I've assumed you've unpaused the video. Hydrogen bonding, of course, to both the hydrogens and the OH groups in water. They're absorbed. It's mostly, as we'll see, OH groups that are sticking up from the matrix here. This is an example of the progress of a paper chromatograph. As we'll see later, this is very similar to the process seen in thin layer chromatography. So start with our sample spot on the paper, water moves up, taking samples with it, maybe separating them. I haven't shown any separations there, and you end with your completed chromatogram. Some definitions. The solvent that moves up the paper is called the mobile phase, or sometimes the elution solvent, and the process is referred to as elution. This is true whatever chromatographic system is used. Measurements. Retention factor RF is a relative distance of the centre of a spot compared to the solvent front distance. It's called solvent from distance in the notes, but it's solvent front distance. Now, this is expressed as a percentage. Okay, we all need some TLC, by which of course I mean thin layer chromatography. So watch this video on the process. It's a pretty good video, and review the Learn Sci material again. So it's highlighted in red there. That's something for you to do. This video makes the process look quite straightforward. It does create quite a lot of skill, however. In particular, successfully producing a small concentrated spot of sample needs practice. This is quite important. If the spot is diffuse, poor results will be obtained. So have a look at that video there. Well worth having a look at. Okay, so TLC plates. We used to make them ourselves on glass backing. These days, thankfully, we buy them ready-made. TLC plates are often a thin layer of silica, SiO2, silicon dioxide, on an aluminium sheet. Again, hydrogen bonding plays its part, with OH groups on the silica surface exposed to the solvent. This is somewhat more complicated than for paper chromatography, as we will see later on, and it depends a lot on the solvent system you're using. Moving on. A number of forces listed here are potentially involved. You'll need to make sure you understand hydrophobicity, hydrophilicity, and polarity, and van der Waals forces, a bit less the latter, before we proceed, and you may wish to stop the video and check your knowledge. Okay, I'm assuming you're back. The OH, which sticks up into the solvent, is a polar group, so will attract other polar molecules more strongly than non-polar ones. This is key and is the basis for the understanding of the separation processes involved here. So here's a question. Again, pause the video while you think about this. Which will move faster up the plate? Strongly polar substances or weakly polar substances? Okay, so I'll assume you've had to think about that and restart the video. Strongly polar substances bind strongly to the silica surface, so will take longer to move up the TLC plate. Conversely, weakly polar substances are bound weakly and move relatively quickly up the plate. So as you can see there, the spots that have moved fastest have decreasing polarity compared to those that have moved slowest. As in many analyses, method development is the most important part of the process. Here this focuses on the choice of stationary phase and mobile phase to ensure an efficient separation. And we've got examples of poor separation and good separation there. Just a quick clarification, a couple of words. The process here is adsorption, not absorption. Adsorption is the adherence of molecules to a surface. This process creates a film of the adsorbate, the molecules or atoms being accumulated on the surface of the adsorbent. And it differs from absorption, in which a fluid permeates or is dissolved in a liquid or solid. And there's some examples of various TLC plate coatings there. The mobile phase will influence the separation in a number of ways, and again it's an important choice in method development. If it is strongly adsorbed at the silica, it will displace the sample, which will move more quickly up the plate than it might do otherwise. In a well-designed system, this will lead to an effective and relatively quick separation. On the other hand, if the mobile phase is weakly adsorbed, the sample will move slowly up the plate, leading to poor separation. Okay, just some examples of common solvents. There's a gigantic amount of literature on these systems. Okay, moving on. Yeah, and just to reiterate, the key is successful method development, given that the actual analysis is often quite straightforward. Here's Richard Willstatter, one of the heroes of food science. He used TLC to separate and identify key molecules like chlorophyll and carotenes. Here's an image summing a Nobel Prize-winning effort. Willstatter was admirable in many ways. He was a German Jew who was asked by Hitler to take charge of a program which eventually led to the development of the German program for an atomic bomb, and Willstatter politely declined and retired to Switzerland long before the real problem started. Okay, so column chromatography. How are we doing for time? Yeah, I think we'll have a break here. We'll come back in a second, in the second part of the video.